that comes from diagrams of two vertices. But as you get further on, you're never going to be able to get a concrete handle on it. So, so you really want to try to study things. Because we don't know what these changes of coordinates can be like, we might as well assume they're arbitrary, and we'll try to study things that are independent of arbitrary coordinate changes. So the orgy flow is a vector field which looks like h bar c squared d by dc plus maybe h bar squared c cubed. So if we choose a scheme, so we choose a coordinate, then the orgy flow is some vector field whose leading order term we computed, and the higher order terms are very hard to compute. The higher order terms, for instance, if I wanted to have a c cubed term, maybe there might be a term coming from this diagram. It's c cubed because there's 3 vertices, and it's h bar squared because it has 2 loops. But so if we look at this, you see it's kind of obvious that these higher order terms will change when I do a coordinate change. So when I change scheme, if I change c by this expression, the result will leave this part fixed, but change the higher order terms. So changing c leaves c. Remember, we're going to allow changes which go c, well, the leading term is fixed, but the higher order terms can change. This will fix. But changes the higher order terms in an arbitrary way. So that means if I'm free to choose my change of coordinates to be of this form, but arbitrary, I can make the higher order terms be whatever I want. So that tells us that there is no scheme-independent data in the higher order terms. So these are entirely scheme-dependent. So just to say the same thing a little abstractly, a little more abstractly. So the manifold of theories it's also a germ of a 1D manifold with a vector field B plus a critical point of the vector field of the vector field. And there's one more piece of data. So because the changes of coordinates always send c to c plus c squared, the linear term in c is always fixed. So we can think of that as a tangent vector at the critical point. Or equivalently, it's a first-order germ of a coordinate. So the only coordinate-independent data you can extract from this is, the coefficient of c squared dc. Okay, so this is in this example. Of course, there's, people who have a math background will be aware that there's a whole field of dynamical systems where people study invariants one can build from vector fields and manifolds. And on one manifold is kind of trivial, but if we had two coupling constants, you could imagine situations where the vector field had some kind of interesting behavior, and you could extract a little bit more coordinate independent. Okay, any questions about this?
So yeah. This is barring the possibility that you could somehow resum the whole derivative series.
Absolutely, yeah. So suppose for some magical reason you had a better understanding of the global space. Then you might be in better shape. You might have a compact one manifold with some number of critical points and flows between them. And then there's much more data. And there are some situations where you can do this.
What kind of situation?
The only examples where I feel I have a good feeling for them are 2D integrable field theories. So where the integrability is some super strong constraint, and there's a kind of geometric understanding of the whole space. Like there's some beautiful work of Zamenlogikov in the 80s, 70s about this, like something called the staircase model, where you flow. There's these minimal CFTs in 2 dimensions, like the WN minimal models. They have perturbations which are integrable, and he studies the flows between them, and he gets some kind of exact answers. Okay, so let's move on. I wanted to I probably mentioned this last time. So if we have a general theory, just say bosonic theory, simplicity. And which classically is scale invariant. Then we can consider quantizations. And then if just like in the 5-4 theory, it's like if we ask that I lambda of L has a logarithmic as lambda to 0 or lambda to infinity. So then the space of such is equivalent to non-canonically the space of scale-invariant Lagrangians. So I think I probably mentioned this last time. So if you could also ask that it has, say, logarithmic plus polynomial growth as lambda goes to infinity, then you will get the space of such is isomorphic to the scale invariant plus things of negative weight under scaling. And if you wanted to have polynomial decay as lambda goes to infinity, you will have the opposite notation. Let's see. Here's a useful, I want to move on to the two-dimensional theories, but I'm going to use this fact. And a useful technical fact so this, as a function of lambda, is a polynomial in lambda, lambda inverse, and log. You don't get, so as a function of this kind of orgy scale, you don't get any crazy functions. So this is a bit funny because the counter terms might have crazy functions in them. But when we scale in this way, we don't. So let's look at 2D scalar theories for a few minutes. Suppose we had fields well, so this Lagrangian especially if you look at it like this way, is scale invariant even if I give these guys dimension 0. Well, so you can play around a little bit and try to think about what is the most general scale invariant thing I can write down. So because these guys are of dimension 0, I can take something like this and add on any polynomial of phi's in there. So the most general scale invariant thing, which doesn't break the SO2 symmetry, actually, I suppose, let's see, is this most general? So I didn't think through this carefully at the beginning. Certainly the most general scale invariant Lagrangian has to have two derivatives, just like this one, and an arbitrary polynomial of phi. Maybe I'm missing some possibilities, but let's not worry about that one. So a general class of scale invariant Lagrangians is given by an expression like this: Bij of phi d phi I wedge star d phi j. where Gij is some function of this phi with no derivatives. Well, so what's this expression? I mean, what we should do is we should interpret this function of the phi's as a metric on the n-dimensional space, which is the target of the phi's. So if we view as a map from R2 to Rn, we're saying that the general scale-invariant thing, then this is the sigma model for some metric G on Rn. Okay, so there's something funny happening here. So if we study the terms we can add on to make a scalar field interact in an arbitrary dimension, in dimensions above 6, there's nothing we can do. And in dimension 6, there's one thing. In dimension 4, there's one thing. But in dimension 2, there's this whole crazy infinite dimensional space of things, of ways we can make a scalar field interact and still be scale invariant. So we found that something kind of bad happens.
Should we worry about J possibly vanishing?
That's a great point. I should have been clear about that. You want G to be invertible, otherwise the kinetic term in the Lagrangian is bad. We find that this scale invariant classical Lagrangians contain all metrics on Rn. In particular, we had this very nice picture in 4 dimensions that once we imposed this condition about logarithmic growth, there was a one-dimensional manifold of theories. So here we find that there's an infinite dimensional manifold of theories I of L, where I lambda of L has logarithmic growth at lambda equals 0, lambda equals infinity. So the paradigm in higher dimensions is always that we should never specify a theory by choosing a scheme. We should always specify it by some more scheme-independent properties, like how it behaves under the order of flow. And things work out very nicely in dimension 4. This tells you there's a one-dimensional space of theories. But here it just completely breaks down. So in particular, this tells you that, if you give me a random manifold, there is no meaning to the sigma model on that manifold. It just makes no sense. If you give me, a manifold with some crazy metric, there's no meaning to the sigma model of that manifold because in different schemes you will change the metric in an arbitrary way, and there's no way to control those changes. So the only settings where you really can talk about this sigma model in a meaningful way is when you have homogeneous space. See, this is a point I find difficult to understand in string theory because, if you take a Clavier manifold, people talk about the sigma model in it, but that doesn't really make sense. I mean, you could imagine supersymmetry helping you out a lot. You might ask, supersymmetry might prevent a lot of these counterterms from existing. That might be good, but it's still a very subtle point, and I don't think it's been. I haven't seen it really clarified in the literature. Okay, so on flat space, things break down. The target is flat. But things are better if we take the sigma model on some or 2x, where x is a homogeneous space for some Lie group. So the best situation is when X is a Riemannian symmetric space. So for example, a hyperbolic space, sphere, so on. Because in this case, there is one metric. One metric up. One G-invariant metric up to scale.
Sorry.
Mm-hmm.
So why doesn't Ricci flatness suffice for the target?
What's that say?
Why doesn't Ricci flatness suffice for the target space? I mean, just the condition that the beta functions vanish.
Well, Ricci flatness is only the condition that the one-loop beta function vanishes. So even if you take the non-supersymmetric sigma model on some Ricci flat manifold, it's not known, and it's almost certainly false, that you can choose counterterms to make it a CFT. It's very hard to construct a CFT in perturbation theory like this, so that all of the terms in the beta function vanish. I mean, you can kind of see why, right? Because you choose Ricci flatness to cancel the first term, and then you compute the second term, and maybe you carefully tune things to cancel that one, but how do you know you can cancel every single term?
So you're saying that's a potential issue for the superstring?
Pardon?
So you're saying that's a potential issue for the superstring?
Yes, although in that case, you also have supersymmetry, which will be a very good constraint, but it's still a point I find personally confusing.
Why is it okay to study like translation invariance?
And the target?
Translation invariant metric on R.
Well, that would be free,
Oh,
because it'll be a constant coefficients. And if you consider like SON invariants, you still have the arbitrary function of the radius. Okay, so now we understand this. So let's try to figure out what the one loop beta function looks like. What does this flow do at one loop? And there's this famous result of Dan Friedan that the one loop beta function is given by the Ricci flow. So let me try to explain how that works. It's actually, if you do it in a kind of lazy way, which I will, it's pretty easy. Because you work in some local patch and you just compute things there. But if you're really careful and worry a lot about what happens when you do some nonlinear change of coordinates, it becomes quite more difficult. So suppose we have X, Riemannian manifold. When we consider the sigma model, whose fundamental field is a map from R2 to X, where the Lagrangian is integral that kind of thing. So in local coordinates, it looks like Gij, some polynomial function of sigma times d sigma I y star of d sigma j. Now, we'll analyze the beta function in local coordinates on the target X, or we're going to choose Riemann normal coordinates. So in Riemann normal coordinates, the metric, Dij, is delta Ij plus a quadratic term which is quadratic in X This is the Riemann curvature tensor at this point. So probably nobody cares about exact conventions about how you index the Riemann curvature tensor, and I wasn't not very careful about it. But the important point we're going to use is that when the Ricci curvature is given by contracting these two indices. So you can see that's the same as differentiating with respect to these guys. So the Ricci curvature, and here I mean the Riemann curvature tensor, look how it's going, at P. So this is given by sum del xk times the metric evaluated at P. Because what do? I take the metric and I differentiate it twice. That. Yeah. So what we'll do is we'll compute the beta function and find that one of the terms, like the leading term, is we change the metric by adding on the Ricci tensor at that point. So this is the point at which I'm being lazy. If you're more careful, you would have to think about, you want to have all of the Taylor terms in the Ricci curvature. But I'm not going to do those, I'm only going to do the leading term. Now, on a homogeneous space, this is enough because the symmetry constrains everything else. Or at least on a symmetric space. Let's compute the one-loop beta function. So the Lagrangian looks like integral d phi I, write it like this, Laplacian phi I, plus the next term looks like this one, phi k phi L d phi I star d phi j times the Riemann curvature tensor. Like so the way it works is you expand the metric as a series in the coordinates, and then every time you see an x, you plug in a phi, and every time you see an ij as the metric index, you have d phi I or star d phi j. So these higher order terms will not be relevant for us. We're only going to focus on this term. So the propagator is the integral from t equals, say, epsilon to L of the heat kernel, which is t to the minus n over 2. So n is 2. That's t to the minus 1. So if we send epsilon to 0, L to infinity, we find the propagator becomes log y. You can just see this by the dimensional analysis. So let's think about the interactions. So we have this 4-valent vertex, possibly higher order terms too. But you notice the vertex depends on the fields in two ways. Some legs have a derivative and some legs don't. So we'll write our vertex using this kind of notation. So this will mean phi I, phi j, phi k, d phi L, y star, d phi m. So the ones where the legs which have the derivatives on them, I'm drawing an outward arrow. That, and the legs which don't have a derivative, I'm drawing an inward arrow. So let's think about what one-loop diagrams can be logarithmically divergent. Well, for instance, if I do something like this, where I move around in a loop, this cannot be logarithmically divergent, because let's compute the propagator. So this guy, because I have an outgoing guy here, I'm going to apply a derivative to the propagator. So this will give me something like, well, integral t equals epsilon to L del y because this guy goes from this one vertex to itself, this will be at y equals 0. And now you notice the derivative will pull down a y, which will vanish. So this won't continue. So by this kind of argument, you can convince yourself that anything where the propagator is attached to something with an outgoing edge, like this, cannot be logarithmically divergent. And the very first diagram you find that is log divergent is this one. So let's think about what this one is. So I'll put some indices. This maybe have K and L. And here, because the propagator will have the same index, this will be I and I. And the coefficient of the interaction is the value of the Riemann tensor at this point. So this is going to be or IIKL integral d phi k wedge star d phi L, these guys. And the propagator will contribute something. This edge, there's no derivatives. So I just take my propagator and I evaluate it when both legs are the same. And that means I put y equal to 0 in that formula. So I get the integral times the integral t equals epsilon to L of t minus 1 dt. So yeah, everybody reasonably happy with this? So to reiterate, so this is the propagator. I've dropped the exponential factor because the two legs are evaluated at the same point, so it's y equals y prime. And the contraction of the indices was given because the propagator is, the kinetic term is phi I, phi I. So what I found is that the first one loop logarithmic divergence is is equal to the Ricci curvature P integral d phi k wedge star d phi L times log epsilon. There may be higher order terms. I'm not too worried about that. We're just looking at the very first term we meet. But this is exactly what we wanted, because now if we run the orgy flow, we scale epsilon, we're finding that we're going to change our original metric by adding on the Ricci curvature at this point. Because this is coupled to the field phi just like a metric would be. Like d phi k, d phi l. So the one loop orgy flow sends metric Gij to Gij plus higher order terms.
Sorry, this is what you worry about true outcome things together.
For the same reason, because that would involve two derivatives, and it would maybe the two derivatives would give you something that doesn't any y's in it, but it would bring down 2 powers of t, and then the integral it would not be log divergent anymore. Okay, any questions about this? And again, so I think like the main point is it's super simple. Just kind of track things like this. You see the Ricci curvature. It's nothing really deep.
So choosing the constant curvature spaces, or rather the symmetry, this just should end up like on theory space. The RG flow should still end up being a one-dimensional manifold, right? Because
yes,
there's only the curvature scale, isn't it?
Exactly, that's right. For Fermionic symmetric space, absolutely. Yeah. So. So, for example, if we take the 2D sigma model on Sn, so because of the symmetry, there's only one term I can add to the Lagrangian. So I don't actually have to compute these higher order terms, which I dropped, to fix that one term, just by symmetry. So this argument, now, of course, on the sphere, the Ricci curvature, so here, like, the Ricci curvature of the sphere is, the scalar curvature times the metric. Just by symmetry reasons, again, the Ricci curvature has to be SON plus 1 invariant. And the scalar curvature is constant. This is just some constant times the metric. So this argument tells us that there's a 1D space of good theories given by the size of the sphere the one loop orgy flow scales the sphere. So the one loop orgy flow is some trajectory which moves along in this one-dimensional space. It's a little different from what we had before, because you might think, like, in this one-dimensional space, where is the fixed point? What's the free theory? The free theory is when the sphere gets infinitely large. So, for example, we could so it's a little more subtle than the cases we had before, because for the free theory, when the sphere becomes infinitely large, the symmetry group is different. The symmetry group degenerates to from SON plus 1 to SON symmetric product or n. But you can analyze what happens when you do a small perturbation away from the infinitely large point, and you find sorry, I feel I should know this. I feel stupid of it. I think it's asymptotically free. Do you remember? Yeah.
The ON non-reducible model?
Yes.
Yeah.
Yeah. Yeah.
I think Polygon.
What's it?
I think Polygon.
Right, but I mean, it's an issue of the sign of the curvature appearing in these calculations. Tells you if it's asymptotically free or not. Right.
Yeah. Well, it's the ON.
It is the ON model, or O1 plus 1 model. Yeah. Okay. So, yeah. So this model is then asymptotically free. So in the UV, you're going towards the infinitely large sphere, and in the IR, the sphere becomes small, and the theory becomes massive. Any other questions?
So is there any sense in which the redundancy in principle in the general single model that has to do with the changes in coordinates can be related to the, I don't know, scheme changing redundancy in the IG or
No, that's let's see. They're not the same. There's two things. Suppose I have suppose I have a field theory which has some nonlinear space of fields. Then to analyze it, I must make two choices. I must choose a scheme and choose a linearization, because the Feynman diagrams depend on the linearization. You can see this in finite dimensions. If I change coordinates, my Feynman diagrams get mixed up in some way. So they're really two independent choices, but of a kind of similar nature.
So, saying if we had this theory of did an experiment like some finite entity that would look like a single model internet and UV was free.
Yes.
So we just run into problems in the IR. Things just go.
Well, it looks like a very, very small sphere. These are interesting models because these are an example of the integral models that people can solve exactly. So there's kind of various phase changes people analyze and so on. For instance, in the UV, the vacuum is when your lowest energy state, maybe when your field hits a point. But in the IR, the lowest energy state is when your R2 is wrapped around the sphere in some quick delay. It's very small. There's these interesting non-perturbative effects.
Where does the phase change occur?
I don't really understand this very well. I mean, maybe phase change is the wrong word. I mean,
Is there like a critical point somehow? I mean, you said that like one point.
Okay, the thing that's funny in that the non-perturbative thing that people understand that I don't understand is that if you look at the Lagrangian of this theory, it looks massless because normally a mass term would be phi squared. There's no phi squared term. But when you go off in the UV and your sphere is of finite size, then people can show that it is in fact massive.
In the IR.
Sorry, in the IR, yes. how do they do this? There's like papers from the 70s where they analyze it at large n. There's people who use the fact that there's Yangian symmetry. Right? It's crazy. This is how the Yangian was discovered. So that's one of the origins. So, but Zamolodchikov calculated two particles in this model can scatter. And the scattering process is given by some matrix, and that matrix is the OR matrix for the Yangian. And they can use this to understand things about the masses, right? Yeah. So this is very interesting and very difficult, and very, very large literature about this stuff. Okay, any other questions? So maybe I'll just do one more quick example of a fermionic theory in 2 dimensions. So this is better behaved. Suppose we have chiral fermions. So these transform these are half zero forms on C. So they transform as like the square root of dz. And you can also have antichiral fermions. So the Lagrangian for the chiral fermions is psi I d bar psi I. For the antichiral ones, it's psi bar I del psi bar I. But then you can ask, can we build a scale-invariant interaction? And this is kind of differential geometry, complex geometry kind of thing. How can we build a 1-1 form, which is something we can integrate from a bunch of half zero and zero half forms? Like other than what we wrote, I think if you think about it a little bit, the only thing you can do is have 4. So we can have an interaction of the form so in this example, we see that in contrast to the 2D scalar field, there are only a finite number of scale-invariant Lagrangians. So this is a good situation. Even without imposing any symmetry, there's a finite dimensional space of good theories, and you can analyze the orgy flow in this space. So yeah, they're just numbers. You want it to be translation invariant. So here's an example. Which is called the clearing model. I don't remember if this particular one is called the clearing model or the Gross-Nivelle model. They're like basically the same. One is an additional term. In which case the interaction is so this is a fun example. It's also an example of an integral model. You notice the way we've written it down, it has obvious UN symmetry. So this example is also asymptotically free, but I think maybe I will leave the computation of the one-loop beta function to next time. It's not difficult. If you want to do it, it's given by this diagram. Correctly. But you find that the one-loop beta function just changes the coefficient here. So it's a nice kind of one-dimensional flow. Any questions?
Sorry, I wrote this wrong. I think so.